Let me talk a little bit about axisymmetry and interfaces. As I mentioned, there's option to run axisymmetric analysis. In order to configure a model for axisymmetry, you just say model config axisymmetry or model configure axisymmetry. That means that FLAC2D will know that any geometry that we built will be axisymmetric, and the analysis should be axisymmetric. One thing to remember, the model should coincide with the vertical axis at x equals 0. It's an axis of symmetry. And on this axis of symmetry, FLAC2D will automatically put roller boundary conditions. That's pretty much all you need to know about axisymmetry. The rest of the analysis is the same. And as I mentioned, axisymmetry runs about 2.5 to 3.5 times faster than equivalent 3D analysis. So here are some plots that confirm that. Just calculation time depending on number of threads on the computer. One word about, or a couple of words about interfaces. Remember, we have continuous model, but we can split it in different disjoint block, that those blocks can slide in shear and basically exert shear along the interface, or even normal force, and they can even open and separate. So you use interfaces when you want to simulate joint, folds, bending planes in geologic medium, or any separation between materials. For example, also you can separate foundation against soil, or how foundation can move in soil. And basically all other applications wherever you feel like separation is needed, and there's some movement can be along that interface. Interfaces are characterized by Coulomb sliding and tensile and or shear bonding. This is conceptual picture of how the interface is treated internally. This is directly from documentation. So feel free to go to documentation and read a little bit about interfaces. But essentially, there can be friction along the interface direction. There's tensile and compressive strength in perpendicular direction. And interface can dilate as well. So you can specify properties like friction, cohesion, dilation, normal and shear stiffness, and tensile and shear bond strength to interfaces to fully describe how the materials will interact along those interfaces. And that's absolutely the same logic in 3D. Just in 3D, your interfaces are actually some sort of planes or surfaces. In 2D, it's just lines, but in reality, it's like infinite line in out-of-plane direction. Let me quickly show an example for this. There's one example, irregular stratigraphy. This is just specifically to work with the meshing to help you learn a little bit sketch and how to build complex geometry, but we're gonna go to this tunnel joints example. Maybe I'll come back to this one a little bit later, but technically whatever you could learn from this irregular stratigraphy, it's actually a DXF file. You could also learn from this example. So I'm gonna quickly show how to build mesh for this example, and then we just open results and just run them. We don't have time to really write the data file. Let me start another FLAC2D. So for this one, just watch me because we don't have time to really, we don't have time to practice, but there's will be information in documentation about how to work with Sketch, and there's going to be videos. There's already a couple of videos available about it. I believe on YouTube they were posted. Let me start a new project. I'm going to create Sketch called geometry. And here I can load pre-existing geometry. So let me import the DXF file that comes from like AutoCAD or another program. Let me go to this folder. There it is. So this is my geometry. It's already aligned with 0, 0, but if it wasn't aligned, I can select it and just drag around. I can specify the translation vector. I can specify if it was not an XY axis, I can map it to XY, essentially, planar view, and so on. This is my background, so-called background geometry. It comes from that file. I can quickly create edges along that background geometry. But before creating edges, let me pre-specify what's going to be the size of zones along that edges. I can do that by going here, the point edge tool, and set default edge parameters. And I can see that this geometry is roughly 200 meters by 100 meters. So I think a zone of size around 4 meters in general should be good enough for me. I will densify the central part around the tunnel afterwards. So I'm going to preset the zone length to 4 meters. And then I'm going to press on this A button with edge, which means automatically create edges in Sketch based on this background geometry. And there they are. So zone size is 4 meters here. But here we see that there's tons of little edges. Well, that's how the geometry was created. And zone size is not 4 meters here, because 4 meters cannot fit in this. So what I'm going to do, I'm going to simply combine these edges in one edge in such a way that the zone size will be 4 meters along that edge. Let me start first with this big part. For that, I can select all these connected edges at once by clicking on this button, selecting by break angle, and I'm going to set a little smaller break angle for future. Any value like 25 degrees is fine. And if I click here, it will select me all these edges for me. But I want to combine only this part and only this part separately. So I'm going to deselect part of it. And by deselecting, I'm going to press Control Alt and just actually one thing I forgot to do. Let me do it one more time. So in Sketch, if you click once on edge, when you start selecting or deselecting, it will select only edges. If you click on node, it will select only nodes, and same with blocks. So I forgot to click on edge initially. Let me do it one more time. Select everything and let me try to deselect now. And now it's deselected. And now I'm gonna press combine these edges, but I'm gonna specify higher tolerance. So the new edges will stick closer to the original shape. Then I'm gonna press here. And now it's my new edge with control points. It became a curve that fits to the original shape. That curve is actually called this line with multiple control points that regulate curvature. And the same I'm going to do here. I'm going to select this, but now I'm going to deselect these two edges. Now it's just single edge here, the same here. That's how I can quickly get the desired edge size. Essentially, that's what means geometry building and model. See that break angle selected this piece that I didn't want, very high break angle, something like this. In 3D, of course, it takes much more effort to prepare geometry. In 2D, it's quite a bit faster. And just these two pieces. So after I'm done preparing geometry, we just quickly run data file and we'll stop with my part. So by the way, let's see what, in general, what we have here. We have multiple stratas of soil. We have tunnel and some sort of potentially fault or intrusion of another material here. It's absolutely artificial example. Building a tunnel at this location would be probably wrong decision, because you would expect some sort of failure if you build tunnel right where it intersects, well, at least this geometry. And obviously, it's very large tunnel for this type of tight boundaries. So we created single edges, but out of all those multiple edges, but still in the center here, we have edges with 4 meter size. Let's say we want to densify things. We can select multiple edges at once, like this, and set zone length there. Let's say 0.5 meter here. So much finer mesh, can be much finer mesh. We can also select these edges. And let's say we're gonna say 2 meters here. And we can even specify a ratio, so they got denser, closer to other to this densified part. And we still don't see mesh, but when we create mesh, we're gonna see that it's gonna be much denser in the central region. Let's set zone ratio like 1.05. And you can see that zones got denser here, or discretization got denser. And that's pretty much it. I can just mesh here. The only thing I wanted to do is make sure that I'm using unstructured mesh to not deal with any problems that could be coming from structured. So I'm just going to say this parameter and say mesh now. And that's my mesh. You see it's much denser in this region. One thing I wanted to do, though, I want to create interfaces along these lines. So I'm going to specify particular groups for these lines. Select them. I'm going to say this is my group joint one. And the same I'm going to do for the other one. For this example, I'm only going to go briefly through the geometry part, joint 2. Then for the tunnel, this is my excavation. Let's call it the scuff 1. Then this is going to be my second stage of excavation. And the exterior part, a little bit weird shape, will be scuff 3. That's all with geometry. Then I create zones out of it. And by the way, when I create zones, the groups that I already created go into slot construction. Wherever I didn't assign groups, they will be assigned block 1, block 2, block 3, and so on. But here it's going to be excavation. I create zones. I could save at this point and just say model save geometry. But let's say I want to assign group for material properties. I'm going to click here and create new slot materials. Actually, here. Materials. This is going to be my soil one. This is going to be rock one. Now the tunnel is still going to be in some rock initially, so I'm going to put this as rock 2. You see, it's now at different slot materials. Rock 2, let's call this rock 3. And this material, this one, let's say it's like intrusion of different material here. This is going to be rock 4. So after this, I could do again this assign group faces automatically to have boundary conditions assigned easily later. Now I'm not going to forget to check this one. Assign groups. You see it says bottom, west, east. That's what I was trying to do in previous example. So here I can apply boundary conditions, roller boundary conditions on the side and fixed on the bottom. And by the way, I forgot there will be vertical load applied here. So I wanted to assign a group here. I'm just going to restore the initial project and I'll show you right away. But this is all with geometry. Next step would be material properties, excavations, and interface properties, and then just cycle it to equilibrium. So that's how you typically approach a bit more complex models, a bit more complex geometry, but the whole picture is kind of the same, I would say, or strategy. So let me just open an existing project. I'm not going to even save this one. Already memory, so results. I'm just gonna open this one. Discard what I already have. So these are my results. Let me hide project commands and this so we can see what we got here. Let's briefly look at the data file. So that was the geometry that I created. I forgot that I also have a load going over here on top, let's say simulating traffic load or some construction. Initially, I will specify gravity, so everything will deform under gravity. I specify properties to all 4 rock domains and soil. And by the way, this 4th rock that kind of simulates this intrusion here is very soft, so it's going to plastically deform very quickly. Then I specify interfaces. So let me actually restore the initial state. And here, in the geometry state. So you can see this interfaces are specified along these lines. Now if you go to initial state, you can see even by gravity, rock starts sliding along the interface. You can see these are the arrows that show how the rock slides. And there are actually 2 nodes on the interface because it's got separated. One node slides down and one slides in normal direction. So this, I'm plotting velocity vectors on the boundaries, and also I'm showing this plot shows interface shear state. You see the red one, the slipping, there is a current slippage happening, and green one, there was slippage along this interface in the past. But otherwise, also by the way, you can see that there's different color scheme. I changed the color scheme and the color plot. And this shows contour of displacement vectors. Sorry, contour of displacements. Let me just quickly run this whole model and we'll watch the results. What's happening? I'm gonna zoom it in a little bit. And this is plastic state. So even initially under gravitational stresses, we already have shear failure in this soft material. We'll just watch how more failure develops around here. The rest of the steps are pretty much similar to what we already learned. Boundary conditions, initial conditions, I'm tracking history. And then I'm excavating 3 stages of the tunnel. It's zone relax excavate command. And then I'm applying top load after all the excavations with zone face apply vertical stress over here. So you probably don't see it. See, I applied over this range on the top boundary. Okay, so let me just run this whole model. We'll see what changes here. So it prepares geometry, analyzes it, and we'll see this thing equilibrating to initial conditions. The unbalanced force goes down. Then material properties start reducing here in the central part. We can see a lot of slippage happening along the tunnel, and the central part got removed. I'm tracking displacements here on the bottom, on the top, and at this point here, we can see that there's already slippage and sliding start happening along this interface. And a lot of plastic deformations developing. Second part of the tunnel got removed, but things are relatively stable there. The maximum displacement is on the level of 1 centimeter right now. Kind of acceptable. Third part got removed. Maximum displacement was still small, but when I applied that top load, very heavy, look how the maximum displacement jumped. 33 centimeters right now. So I'm using SI units here. Again, it's an unrealistic model, but it just shows you how things can change significantly when you apply different load from the initial conditions and how things can slide along the interfaces. But the model equilibrated. Essentially stopped at 33 centimeters. It's probably not acceptable in real engineering situation. We can see, let's look how much failure is happening here. Pretty much this whole soft material failed. plastically, and this part failed plastically. Remember, it was also soft. It failed in the past, though. There's no current failure. That's why the model is stable. All the stresses return to elastic regime. That's how I track displacements at 3 different locations. You see this jump and this jump corresponds to tunnel excavation, and the last jump, it's when I start applying the stop load right above the tunnel. And it starts basically pushing that soft material along the interfaces. Unbalanced force, you see basically everything calibrated. Let's look briefly what happened here. Because it's large deformation, we can see that material, let me hide the displacement vectors. It actually shifted through. You see it's separated here, and this central part protruded through the tunnel by 33 centimeters. So that's what you can do with interfaces. You can also see that there was a lot of slippage, probably even some tensile failures and so on. And you can track all the velocities. You can show the original geometry if you want. Displacement vectors, you can show displacement vectors only on the boundaries or even throughout the whole model. But these displacements here, they dominate the whole model. See, they're much bigger than anything else. And the whole displacement field is, I mean, it's all dominated here. I think that's all for my part.